If you've been tracking the latest papers, you've probably noticed a quiet but massive shift in how we scale large language models. For years, the rule was simple: more parameters, better performance. But dense models hit a hard ceiling. Adding more weights didn't just slow training to a crawl, it also made inference prohibitively expensive. That's where mixture of experts, or MoE, comes in. And if you want to understand where modern AI research is actually heading, you need to look past the marketing and see how sparse activation is rewriting the scaling laws. Let's start with the core idea. In a traditional dense transformer, every single token passes through every single layer, and every layer processes every parameter. That's compute-heavy, and it doesn't scale linearly. MoE flips that. Instead of one monolithic feed-forward network per layer, you get multiple smaller networks, your experts. At any given step, only a subset of those experts actually processes the token. The rest stay completely inactive. That's sparse activation, and it's what lets you pack billions of parameters into a model while only using a fraction of them per forward pass. But here's where it gets interesting. How do you decide which experts to route to? That's the gating mechanism. You'll see two main approaches in recent research. The first is soft routing, where the gate outputs a probability distribution over all experts, and the token gets a weighted sum of their outputs. It's smooth and differentiable, which helps with training stability. The second, and what you'll see in most production systems now, is hard routing. You pick the top K experts with the highest gate scores, zero out the rest, and only compute those. It's faster at inference, but it introduces a sharp discontinuity in the gradient landscape. That discontinuity creates a major training problem: load balancing. If the router learns that expert 3 is slightly more effective, it'll start sending everything to expert 3. The others starve, gradients vanish, and you get expert collapse. To fix this, researchers introduced an auxiliary loss function. It's a soft constraint added to the main objective that penalizes uneven expert utilization. You'll often see it formulated as a combination of the router's output entropy and the actual token distribution across experts. The trick is weighting it correctly. Too high and it fights the main task. Too low and you're back to collapse. Modern implementations use dynamic weighting or gradient clipping to keep it stable. Now, let's talk about what happens when you actually train this at scale. You're no longer just optimizing weights, you're optimizing routing decisions across thousands of GPUs. Communication overhead becomes the bottleneck. When a token gets routed to an expert on a different node, you need all reduce or gather operations to pull the expert weights, compute, and scatter the gradients back. That's why recent architectures use expert parallelism, where each expert is sharded across a dedicated set of GPUs, and routing is handled through optimized collective communication patterns. You also have to deal with expert capacity limits. If you route too many tokens to a single expert in one batch, you hit the capacity factor, and tokens get dropped or delayed. That's why you'll see researchers experiment with dynamic capacity allocation and routing buffers to keep throughput consistent. But the real payoff shows up at inference. Because only a fraction of the parameters are active per token, MoE models can deliver massive throughput gains. You're not paying the memory bandwidth penalty of loading terabytes of weights for every single forward pass. The KV cache only scales with the activated parameters, not the total model size. That's why you'll see MoE architectures dominating inference-serving benchmarks, even if their latency per token doesn't always beat dense models. They're built for throughput, not single-query speed. And if you're working with long contexts, you'll notice that MoE actually helps with cache fragmentation. Since different tokens activate different experts, the memory layout can be optimized to keep active experts co-located, reducing cross-device transfers. If you're diving into the recent literature, pay attention to how routing is being refined. You'll see papers exploring learned routing thresholds, temperature scaling on the gate softmax, and even reinforcement learning to optimize routing policies for specific downstream tasks. There's also a growing body of work on dynamic MoE, where the number of active experts changes based on token complexity. Simple tokens get 1 expert. Complex reasoning steps get 3. It's a step toward adaptive compute allocation, and it's exactly where the research is pointing. MoE isn't just a trick to squeeze more parameters into a model. It's a fundamental shift in how we think about compute efficiency, routing optimization, and scalable architecture design. The papers coming out this year are already moving past basic top K, gating into continuous relaxation, gradient-aware routing, and hardware-aware expert placement. If you want to stay ahead of the curve, start by reading the training dynamics papers, not just the benchmark releases. The real breakthroughs are happening in the optimizer, the router, and the communication stack. That's where the field is right now. Sparse activation is no longer experimental. It's the backbone of the next generation of efficient, scalable models. And if you're curious about how routing policies are being optimized for real-world workloads, or how hardware architects are redesigning interconnects to handle expert parallelism, there's a whole layer of research waiting to be unpacked. I'll leave links to the key papers and open-source implementations in the description. Dive in, test the routing mechanisms yourself, and see how sparse compute is actually reshaping what's possible.